All right, today we're going to be looking at 4.6, linear approximation and differentials. This is a good read. It just kind of talks about, we're going to be looking at a smooth curve and we're going to find the tangent line. And then if you were like to zoom in closer and closer, the actual graph curve line approaches the tangent line. So as you get closer, taking the derivative or finding that tangent line get you really close, and so we're going to use that to approximate points. Over here is just showing you that if you do a rigid curve that's at a point, no matter how much you zoom in, it continues to look like a rigid point, and so that's why we say those aren't differentiable. That's part of it. We can't approximate it if the function is not differentiable. Here is the process of linear approximation. It's showing you the formula. It's basically point slope form. You have a y minus a y1 point. We're using the notation f of a. And then you have x minus that x1, so that's that point, and then f prime is your slope, which we know the derivative of the function at a point is the slope of that tangent line. So it's pretty much point slope form. We're going to call this new function Lx, which is a linear approximation. Here is just the definition. You have a function on an interval I, differentiable, linear approximation. Lx is the y value. So this is when I have it solved, plus slope times x minus x of a, or x minus a, that other x value. Here are some just examples that to kind of show you, good to kind of read over and view these. I'll be modeling some of this in my math lab in the homework section. Here it kind of talks about some of the errors that you will observe when using the exact formula in the approximation. And then here are some other approaches using trig, applications. A little bit about what you can notice with approximation is that if you have a concave up graph, your tangent line is going to be below the graph, and therefore it will underestimate the actual value, and that's kind of what you're seeing here. If you have a concave down graph, your tangent line will be above the line, and therefore it will overestimate near that value. So those are some things you can notice. Here again are some more examples. Good reads and things to kind of look over and make sure you can follow. And then we have a variation of the linear approximation. We're going to introduce delta y and delta x. We also say change in y, change in x. So here is a simplified condition. The change in the y can be approximate the slope times the change in the two x values. And so then you get to see some examples of that. So here's what they're showing you. We have some value, let's just call it 1, and we're going to 2. We don't know what that is. The difference is 1. And so you'll have a y value that's associated with that first x value, and then you'll have another y value. The difference, the distance between here is what we're calling change in y, and the distance between here is change in x. You find the tangent line, and then this formula will approximate the change in y based on the tangent line and the change in the x values. And then again, here's examples using that formula, approximating it, and then this is just a basic summary, again referring us to, here's the linear approximation formula, and then here is to approximate the change in y when the independent variable changes from a to a plus x. You can use that. All right. right, this is also called differentials, but again, it's just kind of doing the same thing. They're just using different notations, dy dx, but it looks the same as that change in y equals slope times change in x. It is saying differentials. Again, you're seeing that same image, okay? The distance between the two x values, dx, change in x. Distance between the two y values, dy, change in y. And then that'll be pretty much the summary. All right, we're going to jump over and do a few problems.